Thank you very much for your patience. My name is Milad, and I'm glad to see so many people join for today's webinar about the optimization of industrial ventilation applications with the use of CFD. First of all, I would like to introduce myself. As I mentioned, my name is Milad. I'm the product marketing manager here at SimScale, and I hold a degree in mechanical engineering from the University of Hanover. I have a 10 years background in engineering simulation with a focus on computational fluid dynamics, and as a part of my role here at SimScale, I'm organizing webinars and workshops to introduce new users and interested engineers to different applications of simulation and CFD. Yes, and today I would like to introduce you to the world of CFD and show you how you can leverage fluid flow simulation to improve HVAC layout and design ventilation applications. And therefore, first of all, we will take a look at SimScale and we will discuss what CFD is, how it can be incorporated and used for application within the AEC industry, and also we will take a look about how CFD can be used in particular for industrial ventilation applications. And after that, I've prepared a short light case study where we will together analyze a design scenario for an industrial plant, and we will create a simulation, take a look at the results, and based on that, come up with a new improved design. Whenever you have a question, don't be shy. We have the question chat box. Just write a question there and I will try to answer it on the fly or during our Q&A session at the end. All right, then I think, yes, we are ready to start. And first of all, I think most of you have a rough idea about what computational fluid dynamics is. And just to put it in a nutshell, so CFD stands for computational fluid dynamics, and it's a kind of numerical experiment where we can simulate the behavior of fluid flows with the help of computers. And CFD has its roots in aerospace engineering and motorsport, and it's actually used for more than 50 years to develop rockets, airplanes, and Formula One race cars. It comes with a lot of advantages. However, in the past, CFD was just accessible to a fraction of engineers due to high costs and upfront investments, which were necessary to perform such simulation. Just to give you an example, 3 or 4 years ago, just to start with CFD, you had to buy a software license, which was very expensive and where you had to pay an annual maintenance fee. You had to buy dedicated computer hardware, and your staff needed a lot of training to get started with the tool. So you were ending up with 40 to 50,000 euro upfront investment before you carried out your first simulation. And 5 years ago, SimScale was founded with the idea and the vision to democratize engineering simulation, make it accessible to every engineer in the world. And the great thing about SimScale is that it gives you full 3D access to engineering simulation through your web browser. And in contrast to on-premise solutions, there is no need to buy any software or to download or to install any software, since everything can be accessed through the web browser in 3D, and all calculations are performed in the cloud. Therefore, you also don't need to buy any dedicated hardware. And the best thing is that SimScale, in contrast to all the other tools, was designed with the focus on a designer perspective. So it's not another tool for simulation expert, but a tool for engineers, designers who want to use it as a tool at their fingertips. And finally, SimScale also comes up with a very interesting freemium pricing model, which means that you can actually use all the features for free, and depending on your needs, there are different commercial packages available, which also comes with enhanced support and other stuff. And just to put it in a nutshell, so SimScale provides you with the all-in-one simulation environment. And inside the SimScale environment, on the one UI, you can perform structural simulation, fluid simulation, thermal simulation, and even some other advanced stuff like acoustic simulation and particle simulation. And the great thing is that you can use one tool for all problems, and also there's a lot of compatibility between the tools. So you can, for example, use the CFD simulation as the input for a structural calculation and so on. We already talked about the pricing model, and as I mentioned, basically we have a free community plan giving you access to all features. And it's not only that SimScale is cheap and more accessible, but we also have some really nice features which help new users to get started, including our real-time support. We have to integrate the chat in the platform, which connects you directly to our engineers and experts, and you can reach our team via email, phone. And besides standard support, we also provide consultancy. We have a lot of free webinars and trainings like this one, and even some whole courses like our simulation masterclass. And SimScale also is very interesting in the case you are working with a lot of colleagues which are located at different offices. SimScale comes with a lot of collaboration functionality. Basically, from the beginning, we have a large community of 120,000 engineers using SimScale. You can access the public projects, channel out with them, and also if you're working in a company, as I mentioned, with different locations, like you can work together at one project. And I mean, in theory, simulation can be used in all industries, but especially for the AC industry, it has a lot of advantages. Because if you think about it, building, and if you have a building construction process or a project, the biggest challenge here is that actually you are not really going to do prototyping. In contrast to a car or some other, let's say, electronic devices or machine design, usually you just have one try to make it. And whenever you have a big problem or something that's not working, it's associated with a lot of cost. And that's actually the great thing, that you can use simulation at a very early design stage to compare different design scenarios, different what-if scenarios, and it can give you a lot of design confidence and help you to save time and money. And here on the slide, you can see a couple of applications for CFD for the AEC industry. And first of all, we can do basically everything around HVAC system and parts, and that's what we will also talk today a lot about. So, like, we can not only simulate single parts like duct opening, for example, to get an idea about the pressure loss and noise pollution, stuff like that, but we can even simulate whole systems, including the ducting system and the surrounding rooms which are supplied with fresh air. And another application which is very much related to that is improving the overall energy efficiency. And this is very important, for example, when it comes to natural ventilation, which is not so important for industrial application, but for residential one. And there you can use CFD, for example, to understand flow patterns, to understand how your building is interacting with its environment, and to see if and how natural ventilation strategy could be leveraged. But besides everything which is happening inside the building, you can also use CFD for predict wind loads or pedestrian comfort, and for sure you can also analyze thermal comfort inside the building, and you can simulate how the air quality and contamination is inside the building. And this is actually what we want to do today. So we want to use CFD to control air quality and contamination. We will also validate the HVAC system design, and we want to optimize the thermal comfort. And with that, we usually can also improve the energy efficiency. All right, so we nearly talked 10 minutes about CFD and SimScale, so let's get started and talk about industrial ventilation. First of all, I would like to start with some very general thoughts and ideas of engineering simulation. So we will later go through a simulation, and what I tell you now will become more vivid and understandable. But basically what we do in simulation is we have so-called governing equations, which are describing how energy, mass, and momentum are distributed in a fluid flow. And since we are not able to solve these equations analytically, we will do it numerically, which means we will take our fluid domain, reduce it to a lot of control points, and then we will calculate pressure and velocity only for the points. And every CFD simulation basically consists of several parts, mandatory parts, whenever it comes to modeling mechanical ventilation applications. First of all, we have so-called obstructions inside the building. These obstructions are interacting with the flow in the room, and the flow in the room is supplied at some point, like you have inlet and you have outlets where air is removed. And in the end of the day, when you want to play around with your model, that's what you can do. You have different obstruction and room designs, and you can play around with the position and the supply rate of the fresh air, and you can play around with the removal of the exhausted air. Some people are complaining about the audio quality. I'm very sorry. It seems like there are some technical problems with GoToWebinar. This is something we cannot control, and I will try my best. And yes, in the worst case, I will re-record some part of the webinar and add it to the recording. By the way, some people ask if we are going to record this webinar, and yes, this is going to happen, and we will send you, I think tomorrow, a link to the webinar recording. And sorry again for the technical problems. All right. And if we talk about an outlet, we can use different boundary conditions to describe how our model is interacting with its environment. First of all, we can have different flow conditions for every inlet or outlet, which means that we can define a velocity or pressure. And just to reduce some confusion, usually it's possible to describe it both ways, using a velocity or pressure. But due to some other practical reasons, usually you should define a velocity for the inlet and a pressure for the outlet. And whenever it comes to, for example, thermal effects, we also have thermal boundary conditions, which are not mandatory, but we can use them if necessary. That will add for sure a level of complexity, but sometimes it can help. And basically, we can define three kinds of thermal boundary conditions. We can define a temperature boundary condition, which means that a surface, for example, has a defined temperature. And then it can be incorporated into the calculation, and we can even do conjugated heat transfer if necessary. And we can also apply heat generation as a thermal boundary condition. So instead of the temperature, we are defining the amount of energy, for example, 500 watts, and usually application for that is a volumetric source, for example, light or fire. And we have heat transfer. And the heat transfer boundary condition, we basically specify the heat transfer coefficient between our wood face and the boundary face. And we can also model contamination, and I think that's what you guys are interested in the most. And for modeling contamination, we can use passive scalar boundary conditions, which means, for example, at the inlet, we can define with the dimensional number between 0 and 1 how the concentration of the contaminant is inside the fresh air. And we can also define it for the whole domain as a kind of initial condition. And the only restriction here right now is if we use the passive scalar, we cannot incorporate chemical reactions, but usually also for more complex contamination phenomena, there are some workarounds to solve it. And if you are interested in that, just drop a question into the chat. I will try to answer it, or ask one of my colleagues to reach out to you. All right, and now let's try to understand what this means in reality, and therefore we've prepared this short case study for you guys. So this is a case study based on a real industrial case from a customer of ours, and this customer is planning and optimizing industrial plants. And in this case, it's all about a small factory line, a small chemical processing line, where parts are coated using these two coating machines, and then some of the parts need to dry inside the rack. And later, in the part of the hall, we have some working stations where people are preparing and processing the coated part. And the problem is that the chemical substances used for the coating, they release some toxic contamination. And it's important to make sure that this pollution is removed from the air before it can mix with the surrounding air, and that the overall concentration, especially for the working station, but also inside the rest of the hall, is under defined threshold. Because otherwise, it would mean for the client of our customer that all the workers need to wear special protection clothing, which is very expensive. Not only to buy this protective stuff, but also for operating the plant under that conditions. And therefore, there were some inlets and outlets. And the idea was that a draft would catch all the pollution, all the fumes, and takes them out before they can mix with the surrounding air. And we have, as I mentioned, we have two inlets at the opposite direction from the fume production equipment. Here we have two outlets, here and here, and we have additional inlet on this side and an outlet here. And the fume is not only produced at the coating station, there's the main part of the fumes produced, but also at the part rack. And now let's try to understand what kind of problem we are facing. So we have a large working space, and it's not possible to change the overall layout of the office plant because this was an existing building and it's surrounded by other buildings. And we have also no influence on the coating stations because they are already chosen, so all the line is already planned, and it's not possible to change the machine or change something related to that. And basically, we know how many fumes can escape from the openings in the coating stations. As you can see, it's a belt, so there is even an enclosure, but still the fume is escaping. And we also need to consider, as I mentioned, the freshly coated parts, which are producing a small part of fume. And what we actually can change is the inlet and the location of the in and outlet, and we can change the total inlet and outlet mass flow, which means we can not only change the total mass flow at all, but also we can change like how this mass flow is distributed, or the balance between the inlets. And we are modeling our toxic fume using a passive scalar quantity. And for this example, we use generic fume because we know that you guys are facing with a lot of different toxical fumes. And so instead of saying this substance, we are going with a generic example. And in this case, there is a limit which is defined by 0.5. And the maximum concentration, the ideal maximum concentration, especially for the working area, should be even between 0.25. And now we are going to set up the simulation. And for this, we are going to use the SimScale platform. And as a third step, we need a CAD model for our simulation. And you can export it using several tools. We have a lot of customers, for example, using Rhino, and you can also directly upload native Rhino files. But we also offer different exchange file formats like SAP, IGES, STL, or some other native formats as well as Autodesk or SolidWorks. And first of all, you need to upload your CAD model, and before sometimes necessary to prepare the model, like make sure it's watertight or add the inlet and outlet, for example. The second step is the so-called simulation setup, which also includes meshing. And meshing is the process of defining the continuous geometry into small elements, small of this hexahedral cell. And the accuracy of our simulation, so the spatial accuracy of velocity and pressure, depending on the density of this mesh. And as fine the mesh is, as fine as the mesh is, as more accurate is the simulation. And once this is done, you can set up the simulation, and it's pretty much straightforward. It's like saying, okay, I want to drag this material, air, into my room, and you can like, or I will show it to you, like define different inlet and outlet boundary condition based on the phases, and then we can run the simulation in the cloud up to 96 cores, 96 CPUs, and then we can visualize the results and use them for design decision. So let's switch a tab. And this is the SimScale platform. So as you can see, I'm on simscale.com. You can basically click here to sign up. And I will now switch to my dashboard. And here you can see all the projects. Let's just open this Fume extraction project. And as you can see, I have geometry here, and it contains out of 16 solids. Take a look inside. So you can see the working stations, the coating machine. And the first step is to create a mesh with some refinements which were defined. And yes, this mesh was already calculated. It can sometimes take up to 1 hour if you have a very large mesh. In this case, we have around 3 million cells. And once your mesh is finished, you can set up simulation, and therefore you select the mesh first of all, then you define a material. In our case, I just imported from material library air, and then you can define the inlet, outlet, and so on. And once this is done, you just create a new simulation run, and then the simulation is performed on the cloud. And in this case, it took 3 hours on 32 cores. And finally, you can for sure also visualize the simulation results. These visualizations are prepared, and you can also directly calculate area average like the mass flow through the outlets, for example. All right. And yes, I prepared the simulation already, and I will send this public simulation link to you together with the recording after the webinar, so you can take a look at the simulation yourself. But now let's go through the results, and I've prepared some post-processing, so some visualizations. So first of all, let's take at the airflow velocity, or at the velocity distribution. And in this case, I used the parallel flight at the head level of the work, at the chest level of the worker. And here you can, for example, now really see the flow velocity, and you can see like how air is entering the hall. And the first thing we can see is that the flow in this agile is oriented in a way that it keeps fumes away from the working area. But there is some problem. First of all, we have a reverse flow behind the coating area here. And this flow, as you can see, coming from here, it will take the fume and then they will mix here. And also what is a big problem, we have a lot of strong draft in the working region, which will result in uncomfortable conditions for the worker. And if we create now another slide, which is at the center line of the coating station, we can also see that we actually have like different flow regimes which are interacting, because on this slide you can just see a small part of the draft here, but if you go a little bit higher in the other direction, you can see the draft coming out from that inlet. And we can directly see two things. First of all, we have three recirculations here. This is the recirculation that we were afraid of, because it will take fumes from here and mix them here with the surrounding air. But we also have a recirculation area between the coating station, which will reduce the fume extraction, because recirculation and turbulence will enhance the mixing. And also, what is the problem, that the strong draft from the inlet is not able to bring the flow from the coating station. We also have a recirculation here, so a lot of the fumes in inlet side will be trapped. And now we can, for example, use streamlines to visualize more precisely what is happening here. And you can see that the flow is coming from here, and then that we have this work circulation. And the big problem here is that the flow from the coating station goes a very, very long way from here before it's extracted here. And during this long way, together with the erratic flow pattern around the coating station, it will result in a lot of mixing of the toxic fumes with the surrounding air for the work of in the hall. And now let's take the same slide, and instead of velocity, we will visualize the toxic fume distribution. And as you can see, it's actually quite clear. So everywhere where it's like pure green, it's absolutely perfect, the fume or the toxic fume distribution concentration. Everywhere where it's gray, it's not really perfect, but still okay, and where it's red, it's really critical. As you can see, basically right now, it is fine for the working area, but also around the coating station are people which are working, and for here the concentration is much too high. 0.5 would be okay for this region, 0.25 or below is necessary for this region, but 0.75 is undiscussable. And we can also calculate some metrics, and we have a large region with a concentration about 0.5 of 154 square meters. And basically this whole site is completely contaminated. And now we can use the so-called contour of concentration, which we also can create online. And this is like visualizing the closed domain where the concentration is higher than 0.5. And you can basically see that it's like a really big space. Basically all the space between the inlet and the outlet on the left side is inside this high concentration contour. And so as you can see, this concept will not really work. So let's summarize what we can get out of the baseline simulation. So a large part of the factory space is above the safety limit, and this is mainly resulted to flow recirculation between the coating station and the large recirculation which is happening below the south inlet trap for the fume. And now there are some solutions, and one would be to increase the flow rate, which would increase the draft, but this has some negative side effects, so we need more energy, and also the thermal comfort will drop, and sometimes this will also not work because increased flow rate can also increase turbulence and increase therefore mixing. And we could also think about prevent the fume exit from coating station with expansive modifications, but as I mentioned, this is basically not possible because we cannot change it. And what we can also do is relocalize the outlet and put them new to the extractors near the coating station. And that's basically what we will try right now. So this is the new design. And here, as you can see, we changed some small things. So we added local outlets near the coating station, a kind of railroad outlet, and we decreased the flow rate for all the outlets. And now let's take again a look at the results. First of all, what we can see, the draft in the near of the working station is really minimized. And instead of, we have a strong draft only around the coating station. And also what is very interesting, that since we have this local fume extractors, the recirculation and the reverse flow in this area is less impactful. And now let's take a look at the other slide. And here we can see these local outlets are really working well because they're creating a strong draft directly at the opening. And we can also see that the draft coming from the inlet now is really directed well. And we have no recirculation below the inlet anymore. And if we now take a look at the streamline, we can see that basically the fume is directly extracted, and even the fresh air from the other outlet guided to the coating station and directly going from the coating station into the local outlet. So this new design or this new flow pattern is very straightforward, and it's around the coating line. And if we now take a look at the toxic fume distribution, we can see that it's looking much better just directly in near of the first opening. We have a zone where it's a little bit increased, but everywhere else, especially in the working area and also around the machine, the concentration is really below the threshold. And the great thing is that now only 4 square meters, this area, is impacted by a high concentration. You can see T and T. These are the only regions, the only contours where the concentration is too high. And now all factory space verifies the safety condition, which means it can be operated that way without the need for any additional security equipment. Now let's just compare it again, and you can really see, and that's the great thing about CFD, how the small changes make a big difference. So now we have the draft where we want it to be in the near of the coating station, and the big recirculation we had here is not existent anymore. It's gone. And also we have the strong draft directly at the out and inlet of the coating line, which will reduce the concentration. And yes, if we take a look at the toxic fume distribution, it's obvious that the new design is much better and satisfying all criteria. Let's again take a look at the smoke distribution or the pollution distribution, and you can see big difference. Like here actually it's quite dangerous. You cannot walk around the machines, and here you only get into a region of higher concentration when you actually put your nose directly into the machine. So this is really safe. Yes, and overall we massively reduced the region or the space of high concentration. And basically the whole factory space now is safe instead of only the east side. And if we now summarize everything, we did 2 simulations, which cost 2 hours manual time for exporting a periodic card model, setting up the simulation, and analyzing the results. It took 5 hours to calculate the simulation, and we used 150 cores. And in return, we received design confidence, and the risk was managed. We now improved it. We saved a lot of time. Just imagine how much it would cost if you would find this out when you started to further plan the hall based on this layout. And basically the factory space where we were trying safety gear was eliminated. Thank you very much for being with us. It was a big pleasure to be your today's host. I hope you enjoyed the session, and in the case you have questions, feel free to write them down into the chat box now, or you can also contact me by email. My email address is mmarty@simscale.com. All right, seems that okay, Buran has some question regarding the contour part, so let's get back on that slide. Buran, can you specify your question a little bit more? And I will try to answer your question. And in the meantime, just to put it into a nutshell, so when creating the contours, what we're actually doing is that we are connecting all cells where the contour, where the value for the concentration is higher than, in this case, 0.5. And then we are looking for the largest closed surface which we can wrap around the cell. And yes, so this is a contour plot, and basically everything inside this region is contaminated. Then there's a question by Rigor, and he wants to know if we can add convection caused by hot parts, human, and winter heating and air conditioning. Yes, this is possible. And it's actually a quite new feature which we added due to the request of several users and customers. And that's, by the way, another great thing about cloud-based software. We are actually introducing updates every week, and it's the same seamless process, so you never need to do it on your own. And now it's also possible to use this kind of simulations together with convection. And if you're interested in that, you should wait for some weeks, because we will soon announce a webinar dedicated on this. All right. There was a question by Devendra. I don't really understand it. Maybe you can specify a little bit more. Are there any other questions? All right. Seems like everything is answered. Thank you very much for being with us. I hope you have a wonderful rest of the week, and hope to see you soon. Bye.